Yep. So, good afternoon, everyone. I'm going to talk about regression methods that general purpose regression method that I have been working on during several years now. And I'm going to show a very simple application to a scaling law in astronomy. So, as an overview, I'm going to introduce a few challenges related to regression analysis, very well known probably in this community, and make the transition to minimum distance estimation, which sort of sets the stage for the method which we have called geodesic least squares regression. And finally, there's this application in astronomy. So a number of challenges that are well known. Of course, we wouldn't be here if there weren't uncertainty in data due to measurement error, fluctuations in physical systems, but also uncertainty in models due to missing variables, choice of linear versus a non-linear or a whole range of non-linear models, Gaussian, which is the stochastic model of choice usually versus non-Gaussian models. Heterogeneous data and error bars in complicated data sets. Various subsets might have different error bars. There can be uncertainty on response and predictor variables. There are these things like outliers, atypical observations, near collinearity of predictor variables, and then this is something that is often happening in a very relatively naive way when fitting scaling laws, estimating scaling laws in a whole range of fields in astronomy. I'm from the field of nuclear fusion mainly, and biology, geology. Usually what people do is, so they have this power law, which sort of describes scale invariance, and they're going to take the log on both sides, and it seems like it gives you a linear regression problem, but it's can be very dangerous, because actually you should remember that these are not infinitely precise points. They are can be seen as samples from an underlying probability distribution, and so you're going to skew the distribution, and this can lead to a lot of problems. So the workhorse in many fields is ordinary least squares, and it's unbelievable how people that are not, in fields that don't have a great tradition in statistics or data analysis, always still cling to the very safe and extremely simple methods. Some people venture towards maximum likelihood or maximum a posteriori. So this is for the case of a very simple linear model. In general, so this, of course, this rests on a lot of assumptions, many of which in realistic settings are not fulfilled. So what is actually required in many application fields is a flexible but primarily a robust regression method, because robustness in regression analysis, in realistic regression analysis, is, I would say, at least as important as goodness of fit. Robust, but also easy to apply. That is also a very human requirement. If it's not easy, people from application fields are not going to use it. It should be easy, and that's why they always use ordinary least squares. So, going towards the explanation of the method, I'm focusing here on the well-known idea that if you do parameter estimation, actually you're doing some kind of distance minimization. So in regression analysis, with for instance, ordinary least squares, of course you minimize that distance between what you measure and what you predict according to the model. So minimizing that distance between expected and measured. And that's of course also the case here in maximum likelihood. Now this is sort of generalized in what has been called minimum distance estimation. where the focus is more on the underlying probability distribution. So the question can be, which distribution does the model predict versus which probability distribution empirically do you observe? You're going to minimize a sort of similarity measure, a distance measure between those two distributions. So if you're looking at the parametric distributions, which we are going to do, and if you would take a Gaussian, univariate Gaussian case, what you're actually allowing at that point is that the probability distributions predicted and observed do not only have different means, but also could have different standard deviations. So as a distance measure in this case, which turns out to have quite good robustness properties, often the Hellinger divergence is used, and for an empirical distribution, often a kernel density estimate is employed. Okay, so this sets the stage for the method that we call geodesic least squares. And go back to what will probably be the most empty slide during this conference. So we have two measurement points in some whatever abstract coordinate space, whatever, and we suppose that this is the prediction by the model, this is the measurement, and we want to minimize that distance. But then what you can, what you always have actually is that if you zoom in, you see that a measurement which you take is always going to be an average, an amalgam over some microscopic dynamics that are going on inside the system at some smaller scale. And it's that variation that we wish to capture using a probability distribution. So that could, of course, capture a measurement uncertainty, microscopic fluctuations in the system. And I give an example here. So suppose you have turbulent flow through a pipe with a constriction, and you measure the average velocity here. Obviously, it's going to be, on average, smaller than the average velocity here. But on the other hand, if you measure the velocity at a specific point anywhere inside the flow, you're going to see that it fluctuates because it's a turbulent flow. So that gives that picture of variation at a microscopic scale, which we are trying to capture using our model and the regression analysis, versus dynamics going on at a microscopic scale that we are not particularly interested in to model with our regression function, but that is nevertheless there and gives information, useful information, on the properties of the velocity at any particular measurement site. And so that is depicted for one measurement site, as I'm going to call it here. So these are all average velocity estimates. For instance, this is just a cartoon, so to speak. And here we realize that actually we measure at, for instance, if we measure at different points in time at a specific location, we measure different velocities. You could also measure, there is also uncertainty on the width of the pipe. And so it's a bit exaggerated here, but there is also uncertainty here. And you predict this distribution according to the model, you measure that distribution, and you want to minimize that distance to estimate the parameters of the regression function that describes the macroscopic dynamics. So, of course, what you actually do if you do maximum likelihood is you are going to calculate or minimize the Mahalanobis distance between what you measure and what you predict. But this does not allow the standard deviation to be different. It measures the distance between two clusters that have the same standard deviation. So what we are going to do is to replace this by the Rao geodesic distance based on the Fisher information. And at that point, an observation or a prediction, which before was a structureless number, is being replaced at every measurement site by a distribution, a structured object. And this is going to, as we will see, introduce more flexibility and also more information into the method. And I draw here the analogy between measuring seeing the difference between two animals. So what I do not want to do is calculate all the distances between each of the individual points, and neither, if I look at an animal, I'm going to measure the length of the ears, the size of the eyes, and so on. I look at this object and I see a difference. I look at the object as a whole, and I'm going to, in the same vein, I'm going to model these measurements with a parametric probability distribution and calculate the difference between the underlying parametric distributions as a whole. So just as an illustration, because usually in many applications, if you have a single response variable, so it's so a single response variable in a regression problem, often you're going to work with the Gaussian distribution. So I focus here on the geometry of the well-known geometry, of course, of the univariate Gaussian manifold. Well, this is the line element derived from the Fisher information. It describes hyperbolic geometry. Various models are known to describe that geometry: Poincaré half-plane, Poincaré disk, line disk. Useful for computational purposes is that there is an analytic geodesic distance, also well known. I invite you to look at this nice video on YouTube by Frank Nielsen and Richard Nock that gives a nice illustration of all these models. Now, I also wanted to show you this model, which is slightly due to Beltrami, which is slightly less known. Because it models actually only a portion of that geometry, but you can. So this is called the pseudosphere or tractoroid, and the mean is going in this direction. So this model is periodic in the mean, and the standard deviation goes in that direction. So you see that it has negative curvature everywhere, and these are two geodesics. They wind, of course, because the model is periodic, they wind around it, and sometimes for that reason I compress everything in the direction of the mean so that you nicely see the geodesics on the front of the image. Why is this important? Because if you explain the method and to people I'm dealing primarily with physicists, and they want to understand the method. You talk about this geometric interpretation of probability. Many physicists are familiar with general relativity, but they want to see the surface. They think of a surface embedded in a Euclidean space, and this is the way they're going to understand that. So this is the analogy with the Poincaré half-plane. So just as an illustration, some distributions here and the corresponding points on the various models, and then some with larger standard deviation and the same mean. And you indeed see that the ones with larger standard deviation are closer together than the other two. So this is actually in a very simple example of what is actually geodesically squares. So we are going to look at the probability distribution that would be predicted by the model, and I've taken here just a multilinear model with n predictor variables. You're going to look at that distribution. You also see that the uncertainty of the predictor variables propagates through the model and leads to a total variance on the quantity on top. But this distribution you would expect if the regression model were completely correct, also at the microscopic scale. And on the other hand, you want to look at that distribution that is suggested by the data. And I'm going to take here also a parametric model. I'm only going to assume that it is Gaussian, and I'm going to assume, it's a very simple case, you can completely generalize this, but going to assume that this standard deviation is unknown. I call it observed standard deviation, observed distribution, model distribution, and I minimize the geodesic distance between those. And in doing that, so it's a model-based approach, so it's not immediately clear, but actually at that point you're doing regression on a probabilistic manifold to be estimated, the parameters here of that linear model, and this, in this case, single parameter here of that observed distribution. And if you have IID data, you actually can minimize the sum of square geodesic distances, hence the name geodesic least squares regression. And also interesting to note is that if you force the model standard deviation and the observed standard deviation to be equal, the row distance also reduces to the Mahalanobis distance, so it's consistent with maximum likelihood. So that is the method. Very briefly, a simple application, but nevertheless a very important scaling relation in astronomy between the velocity, the rotational velocity of these galaxies and the total mass, the baryonic mass, that means both the stellar mass and the gaseous mass of that galaxy. There turns out to be, quite remarkably, a very simple relation, a power law, and also very tight. And this is a very important relation because it serves various purposes. It can be used as a distance indicator to measure distances as a distance scale. It sets bounds, constraints on galaxy formation models, and it can also be used as to test alternatives for the famous lambda cold dark matter cosmological model. Specifically the slope, and so the exponent there, beta 1, and the scatter around that are of interest. So what we do here, we take data, published data from gas-rich galaxies, and just by way of test, we're going to do this the way everybody in astronomy would do that. So you take the log, and supposedly you get linear regression analysis. So I'm going to fix here that observed standard deviation. I take only one parameter. So I assume a fixed relative error on the mass, because that is my dependent variable, the mass of the galaxy. So I assume a fixed relative error. So one number on a logarithmic scale, and also one number on the original scale. And I'm going to run my analysis and benchmark with a few well-known methods, Bayesian with marginalized standard deviations, which is supposed to be robust also. So geodesic least squares, and just for fun, I also replace the row distance by Kullback-Leibler divergence. In this case, it gives more or less the same result, but not in all cases. So here you see that this is on a logarithmic scale. The standard, so these error bars depict a single standard deviation on the measurement that is given by the astronomers. So this is given. But of course, and that's the flexibility of the method, you are not required to trust this also. Now let's look at this. Something funny happens if you look at this on the original scale. So it looks completely different, and some points that used to lie very nicely on that line. And so remember that the scatter of those points is very important also for astronomical reasons. So some of those points that lie on the line now seem to be almost outliers. And of course you see that ordinary least squares completely follows those points, those outliers. The other methods indeed seem to be quite robust. Well, here they more or less give the same result, but this is a very simple application. There are other applications where, well, turns out that GLS is always very robust in all the tests that we have used it, and even more robust than some of the standard methods. And the nice thing is that it's very simple, and so it takes only a few lines to program this. Closed analytical form for the geodesic distance takes only a few lines to program this, and it's extremely fast. So it's almost as simple as ordinary least squares. Yeah, okay, so the parameter estimate's not particularly interesting at this point. Yeah, I did this using bootstrapping because at this point it's difficult to get error bars because it's an optimization-based method. So I did some bootstrapping, and then you get distributions of the parameters. This is on the logarithmic scale, this is on the original scale, and you see that ordinary least squares goes all over the place with that slope parameter. And then finally, this is actually the reason in this very simple case why geodesic least squares is robust. So internally what it does is, this is on a log scale, so this is the response variable, the mass, and the error bars on the mass. Now these are the original data, the blue points, and let's say the red lines or the red points are the standard deviation or the uncertainty that the GLS method assigns or estimates from the data, which clearly is higher. You don't see it, but it's significantly higher. We start from about 40% on the data, on the masses, but it becomes more than 60% if you estimate it. And this is, of course, because you have these points that have, some of these points have a high deviation from the model, and this is captured by the method by increasing that observed standard deviation. So it's also important useful to estimate the scatter, the real scatter on that relation, which is quite a bit higher than you would naively expect. This is just for illustration, a plot also on the pseudosphere, where again you see that, so the blue points are the data points, the red points are the ones estimated by the method, and so they are all shifted upwards to higher observed standard deviation. So finally, well, I think geodesic least squares regression is a flexible and robust method, provides a unified solution to various issues that I mentioned in the beginning in regression analysis, works for linear and nonlinear relations, in principle for any distribution model. A probability distribution at a microscopic scale, well, of course, in the case of astronomy, this is all relative, but to a certain extent, it's a microscopic scale, provides more information than the individual measurements alone. So so you have to look at the total probability distribution. It's also nice, I think, that you get this geometrical intuition for the regression method. It's easy to use, and it's very fast, so I think it has a lot of advantages. Thank you.
Is there any quick question, because the plenary session starts in 5 minutes, I believe. Any quick question for the speaker? Yes?
So the hyperbolic space is the good model for the Fisher distance between distribution in 1D. But then it's not so simple if we augment the dimension. How do you see the technique scaling up to other dimensions, to larger dimensions?
Well, up to now, it hasn't been really an issue because the dimensionality of the space is determined by the number of response variables. And because we look at the probability distribution of the response variable conditional on the predictor variables. So if you have only one response variable, which is the most common case in regression analysis in applications that I'm working with, you have also just univariate distribution. Indeed, if you're going to look at multiple regression, then multivariate regression, then you're going to have to look at multivariate distributions also.
But then the computational complexity of the Fisher metric is...
But in the Gaussian case, I think it's...
we have no closed form for the geodet.
Yeah, that's true. Yeah.
So that's a little problem.
Yeah, that's true.
All right, so I propose that we close the session here. Thanks for attending and thanks to all the speakers.